Okay, so, you know, when we talk about the Ice Age, like most of us probably picture, those woolly mammoths and cavemen,
Yeah.
it's like this frozen world from a distant past. But here's something that really like shifts your perspective. Technically, geologically speaking, we are actually living in an ice age right now.
Yeah, that's a really interesting point to start with. And it is true. What we typically think of as the Ice Age was really just like the most recent, cold snap, I guess you could say, a glacial period within a much longer ongoing ice epoch. It's kind of like if you think about like being in a really long winter with these like short warm periods like the one we're in now, what we call an interglacial.
Okay, so we need to unpack this a bit because that it really changes things for me. So for this deep dive, we're going on a journey through time. We're not just going to explore these swings between ice and these warmer periods, but we're going to follow the incredible scientific detective work that allowed us to even understand them. We have this book that chronicles this entire discovery, and it is full of crazy twists and turns. We're going to uncover like these hidden rhythms and triggers behind these massive climate shifts that our planet has gone through.
Yeah, and what's really cool is like the sheer variety of evidence that scientists have managed to piece together. You have these geological mysteries, right? Like those scratches on bedrock that just don't make sense based on the local geology. You have these boulders that just seem totally randomly dropped in the middle of nowhere. And then you have this biological record too. These fossils that show how plants and animals adapted and changed over time. Even the tiniest little shells of plankton at the bottom of the ocean, they're like little thermometers recording the sea temperatures of the past. And as we're going to see the movements of our planet in space, the astronomical observations, they really ended up being the key to figuring all of this out.
Right. So our mission today is to trace that scientific journey. Like, how did early scientists even begin to make sense of all this evidence of past ice? And how did they figure out these ice ages happen in cycles? And I guess like the big question, how did they connect these changes on Earth to, the movements of the planets and the stars, those celestial mechanics? It's a story that tells us so much about our planet's climate in the long term, and it all started with some very confused people in the Victorian era.
It's so interesting to see how just a few weird rocks really started this whole journey of discovery. These erratic boulders, I mean, that's literally what they called them because they were so out of place. These big rocks just sitting there, far from where they should be geologically. It wasn't just a few either. Sometimes there'd be these huge, chaotic piles of rocks and sediment just dumped in places they shouldn't be. It was a real puzzle.
And at first, I mean, especially back in the 17th and 18th centuries, the obvious answer was the biblical flood, right? Fit perfectly with this idea of catastrophism, these huge, sudden, often divine events shaping the Earth. The flood was just the latest in a series of these world-changing events.
If you think about it, this whole view fit with the idea that the Earth was only a few thousand years old, which is what many people believed based on religious texts. So they had to squeeze all these big changes, like fossils of extinct creatures, the layers of rock. They had to fit it all into this really short time scale. And what better way than a series of acts of God, right?
Right. But up in the Alps in Switzerland, a completely different idea was starting to form. Being surrounded by glaciers all the time, people there naturally saw a connection between those erratic boulders and moving ice. They saw how glaciers could carry rocks down valleys and drop them off as they melted back. Actually, a Swiss minister named Bernhard Kuhn, he wrote about this link all the way back in 1787. But nobody really paid attention to his ideas at the time. Then, in the 1790s, a Scottish geologist named James Hutton, he saw the same thing in the Jura Mountains and came to the same conclusion independently. But again, nobody really bought it.
So why is there so much resistance to the idea that glaciers could have moved these boulders?
Well, Hutton was also a big proponent of this idea called uniformitarianism. The idea that the Earth has been shaped over billions of years by the same slow, gradual processes we see today. Things like erosion, deposition, volcanoes, not by these sudden, massive catastrophes. So while an ice age might sound like a catastrophe to us, when you think about it in terms of billions of years, it's just part of this long, slow, ongoing change, almost like a cycle. Yeah, that makes sense. But for a while, this whole glaciers move the rocks idea, it just stayed kind of quiet until this guy, Louis Agassiz, came along in 1837. Even people like Charles Lyell, who was a big supporter of Hutton's uniformitarianism idea, he still thought that water was the main thing that moved those boulders around. He was talking about icebergs, carrying rocks, and then floating to those random locations.
Agassiz, he was quite a character. He was trained as a doctor, but his real love was studying nature. And it's interesting that he first heard about the Ice Age idea from another scientist, Jean de Charpentier, who had been convinced by a mountain guide, Jean-Pierre Perraudin, of all people, that glaciers had once been much bigger than they are now. So de Charpentier showed Agassiz all his evidence in 1836, and Agassiz, who had been pretty skeptical at first, he was totally convinced after seeing it for himself.
If you can even call it convinced. Agassiz didn't just accept the idea, he ran with it. He went all in and said that there was this gigantic ice sheet that covered all of Europe. He said it went as far south as the Mediterranean Sea. De Charpentier must have been shocked by how extreme Agassiz's theory was, especially since he was the one who got Agassiz interested in the first place.
You'd think that people who believed in slow, gradual change, like Lyell, would have rejected Agassiz's theory outright. But even William Buckland, who's a big believer in catastrophism, even he wasn't convinced at first, even after Agassiz personally visited him to try and persuade him. But here's the funny part. Some catastrophists actually like Agassiz's idea because they saw the Ice Age as this clean break between different periods of creation. Which is kind of ironic when you think about it.
Yeah, total opposite of what they usually believed. But Agassiz, he was like a force of nature, super persuasive and energetic. He went out and gathered more and more evidence, even doing his own studies of glaciers, measuring how they moved, albeit very slowly. And in 1840, he published this book called Études sur les glaciers, and it just blew everyone's minds. This massive ice sheet, and what it did to life, he described it in such vivid detail, things like the silence of death. An enormous hippopotamus suddenly buried under a vast expanse of ice really captured people's imaginations.
That same year, he went to the British Association for the Advancement of Science meeting in Glasgow and presented his ideas. Lyell was still not convinced at this point, but something changed for Buckland. After the meeting, he went with Agassiz and Roderick Murchison to Scotland to look at the geology there. And seeing the evidence firsthand, that's what convinced Buckland. He immediately went to Lyell to try to get him on board, and within a few days, they found evidence of old glacial moraines near Lyell's own father's house.
Talk about a turning point. By the end of 1840, you had Agassiz, Buckland, and Lyell, three of the biggest names in geology, all presenting papers to the Geological Society. They basically established the Ice Age theory as a core part of science. It's amazing how quickly this went from a fringe idea to something everyone accepted. Though you have to feel a little bad for de Charpentier, whose own research, which he published soon after, got totally overshadowed by Agassiz. It even hurt their friendship, which is sad. Agassiz later moved to America and had a huge influence on science there. But get this, he never accepted the theory of evolution, even until he died.
So once everyone accepted that there had been ice ages, the next big question was, well, what caused them? And that brings us to Joseph Adhemar, this mathematician who wrote a book in 1842, where he proposed a link between the Earth's orbit around the sun and these long cycles of cold.
Okay, this is where it starts to get really interesting. We all know the Earth goes around the sun, but it's not a perfect circle, right? It's an ellipse, a slightly oval shape. Kepler figured that out back in the 1600s. So that means our distance from the sun changes throughout the year, which obviously affects how much solar energy we're getting at different times.
Exactly. And on top of that, the Earth is tilted on its axis, which gives us the seasons we all know and love. Adhemar took this a step further. He knew about the precession of the equinoxes, this really slow wobble in Earth's rotation, kind of like a spinning top that's slowly wobbling as it spins. This wobble takes about 22,000 years for one full cycle, and it means that the timing of the equinoxes and solstices gradually shifts relative to our elliptical orbit.
So Adhemar thought that this slow wobble, together with the Earth's elliptical orbit, was what caused ice ages to alternate between the northern and southern hemispheres. He said that when one hemisphere has longer winters and shorter summers because of how the Earth is positioned in its orbit, that hemisphere would go into an ice age, while the other hemisphere would be warmer at the same time.
It's fascinating how Adhemar was already thinking about these cyclical ice ages driven by the movements of the Earth in space. But his model had some big problems. For one thing, he thought the reason Antarctica was so cold was because of the different lengths of the summer and winter halves of Earth's orbit, which wasn't quite right. He also thought that the massive ice sheet in Antarctica would somehow pull water away from the northern hemisphere, which sounds kind of crazy.
Right, and Alexander von Humboldt, the famous explorer and scientist, he pointed out a big flaw in Adhemar's reasoning. He said that the total amount of solar energy each hemisphere gets over an entire year is basically the same, no matter those little changes in the orbit. So Adhemar's idea that one hemisphere would cool down while the other warmed up just didn't hold up.
So now we come to James Croll. He took Adhemar's basic idea, but he built a much more solid and logical model without all those weird extra bits. Kroll's life story is pretty amazing, actually. He didn't have much formal education, worked all sorts of manual labor jobs, and had health problems. But he basically taught himself science by reading books while working as a janitor at a museum. He really became a serious scientific thinker.
That's incredible. From janitor to figuring out ice ages. What exactly did Kroll add to this whole puzzle?
Kroll's big idea was changes in Earth's orbital eccentricity, basically how much the shape of our orbit stretches and squashes over time, going from more elliptical, which is like a stretched out oval, to more circular and back again. And this happens on a cycle of about 100,000 years. And Kroll said that those periods when the orbit is most stretched out, those were the times when ice ages happened.
And his thinking was that a more elliptical orbit would mess with the seasons, right? He thought those really stretched out orbits would lead to super cold winters when the Earth was farthest from the sun, leading to tons of snow that wouldn't melt even during the cooler summers, and eventually causing these huge ice sheets to grow.
Exactly. Kroll was one of the first to really consider the importance of these things we call feedback mechanisms, like how a big blanket of snow and ice would reflect more sunlight back into space, making the hemisphere even colder. The specific feedback mechanism he had in mind wasn't quite right, but his idea that these amplifying effects were important, that was groundbreaking. He also brought back the precession of the equinoxes into his model. He said an ice age would happen about every 11,000 years, flipping between the northern and southern hemispheres, kind of like what Adhemar proposed.
But Kroll didn't stop there, did he? He knew that the oceans played a big role in climate, too. These huge currents moving water around the globe. And he realized those currents could be affected by changes in the atmosphere, which are driven by temperature differences between the hemispheres.
Absolutely. He thought that if one polar region got a lot colder, it would make the trade winds stronger. And that would change the way those big ocean currents flowed, maybe even reducing the amount of heat moving towards the colder hemisphere. He even considered the tilt of Earth's axis, what we call obliquity. He said if the tilt was smaller, it might make it easier for ice ages to start, because the poles would get less direct sunlight during summer. So by 1875, when he published his book, Climate and Time, Kroll had basically identified the three big astronomical factors that affect Earth's climate: how stretched the orbit is, how the Earth wobbles, and the tilt of its axis.
And at first, people really liked Kroll's model because geologists were finding evidence of repeating ice ages. But the problem was they couldn't date those past glacial events precisely enough to see if they match his proposed 11,000-year cycle.
Exactly. And as we moved into the 20th century, a big problem emerged that would eventually lead to people abandoning Kroll's theory. Scientists were developing new ways to date things, and they were suggesting that the last big ice age ended around 10,000 years ago. But according to Kroll's model, the Earth should have been warming up at that time. Actually, the climate records from between 100,000 and 80,000 years ago seem to be doing the opposite of what Kroll's model predicted based on the positions of the Earth and the Sun. This was a big deal and eventually led to people not believing Kroll's model anymore. But as we'll see, the fact that his predictions were basically backwards, that turned out to be a really important clue.
Wow, so the Victorians did all this amazing groundwork. They figured out that these massive ice ages had happened, and they even connected them to the way the Earth moves in space. But a completely accurate model was still out of reach. And that's where Milankovitch comes in. In the early 1900s, he set out to do something really ambitious: create a detailed mathematical model of Earth's climate based on those three astronomical factors that Kroll had identified.
Milankovitch, he was a Serbian civil engineer, and he was a man with a big vision. He wanted to figure out a complete mathematical theory of climate, not just for Earth, but for other planets too, and across vast stretches of time. There's even a story that the idea for this huge project came to him really suddenly in 1911. His colleagues apparently thought he'd either had too much to drink or had gone crazy to even think about taking on such a monumental task.
But he already had one major piece of the puzzle, didn't he? Those detailed astronomical calculations of those three orbital parameters: precession, eccentricity, and axial tilt, going back 1,000,000 years. Those had been worked out by Ludwig Pilgrim in 1904.
Exactly. Pilgrim did the hard work of figuring out the astronomical data. Milankovitch's job was to calculate how all three of those factors together, and constantly changing, would affect the amount of sunlight different parts of the Earth received at different times of year over millions of years. And remember, this was all before computers, so he was doing these incredibly complex calculations by hand.
This guy was dedicated. The book even talks about his super strict daily routine of work and thinking. And he actually had a big breakthrough in his thinking during the First Balkan War in 1912 while serving in the Serbian army. Even in all that chaos, he was still figuring out the mysteries of the cosmos. It just goes to show that sometimes taking a break from a problem can help you see it in a new way.
Right. Sometimes stepping back can lead to that aha moment. When he got back to Belgrade, he really started making progress with his math, and he even started publishing his early results. Unfortunately, he published those first papers in Serbian, so most of the international scientific community didn't see them.
And then World War I, as horrible as it was, actually gave him a weird opportunity, right? He was interned in Budapest, and that gave him years of uninterrupted time to focus on his cosmic problem, as he called it.
Exactly. For almost 4 years, he had access to the library of the Hungarian Academy of Sciences. It was perfect for him to just bury himself in his calculations. He finally published his complete model in French in 1920, but again, most geologists didn't pay much attention to it. But there was one really important exception: Vladimir Köppen, the famous climatologist.
The same Köppen who created that climate classification system everyone uses, and he worked with Alfred Wegener, the guy who came up with the theory of continental drift. In their book from 1924, they talk about Milankovitch's work. And Köppen had this really crucial insight, didn't he? He realized that it wasn't the super cold winters that were causing ice ages, but actually the cool summers that weren't warm enough to melt the winter snow.
That was the key. Köppen pointed out that even today, it snows a lot in the Arctic during the winter. The reason we don't have a massive ice sheet covering everything is that most of that snow melts away in the summer because it's warm enough. So he said, to get an ice age going, you need summers that are cool enough to let that winter snow stick around year after year. Eventually, it builds up into these massive ice sheets. This completely changed how people thought about the problem. It also flipped the prediction of the astronomical theory. Now, it suggested that around 80,000 years ago, the northern hemisphere should have been getting cooler summers. And around 10,000 years ago, it should have been getting warmer, which would have melted the ice sheets and ended the last ice age.
So with this new understanding of how important summer temperatures were, Milankovitch went back to his calculations. This time, he focused specifically on how much solar heating the high northern latitudes were getting during the summer. And when he plotted the results, he got these curves with dips or notches that showed when summers were especially cool. And those dips seemed to match up really well with what geologists knew about when glaciers were advancing and retreating in the European Alps. Köppen's work also backed this up.
As Milankovitch kept refining his model, he figured out the main cycles of those three astronomical factors: the eccentricity of Earth's orbit, which changes on a cycle of roughly 100,000 years, the tilt of Earth's axis, which has a cycle of about 41,000 years, and the precession of the equinoxes, which has a cycle of about 22,000 years. And each of these cycles affects different parts of the planet differently. He even used observations of where the snow line is at different latitudes to figure out exactly how the amount of summer sunlight affected whether glaciers grew or shrank.
So basically, this turned everything upside down. Now, interglacial periods, like the one we're in now, were seen as the exceptions. They only happen when those astronomical factors line up just right to give us really warm summers that melt back the ice. Otherwise, given how the continents and oceans are arranged today, it seemed like the Earth's natural state was to be in some stage of an ice age.
Exactly. And in the 1920s, 30s, and 40s, a lot of scientists, especially in Europe, were really excited about Milankovitch's model. It seemed to fit really well with the general pattern of ice ages that geologists had figured out, but there were still some big problems. For one thing, the dates for those past ice ages were still pretty uncertain, especially for times before the 1950s. And there was also this kind of circular logic going on, where sometimes people were using Milankovitch's curves to figure out the dates of ice age evidence.
And when they tried to match his very precise calculations with the exact timing of how the ice sheets were moving around 80,000 years ago, it didn't seem to work. This led to a lot of scientists losing faith in Milankovitch's model by the mid-1960s. It seemed like his predictions didn't match up with the geological evidence.
But looking back now, with better data, that evidence that seemed to contradict Milankovitch's model in the mid-20th century, well, it wasn't very strong. The data they had back then was from only a few places, and the dates were uncertain. To really put Milankovitch's theory to the test, they needed a continuous, reliable record of global temperature or ice volume that went back a long way. And they finally found that in the 1970s with the analysis of deep-sea sediment cores.
Ah, yes, the ocean floor. It's like this massive library of Earth's history. You have these tiny sea creatures like plankton and foraminifera, and their shells are constantly falling to the ocean floor and building up layer after layer over millions of years. And get this, different species of these creatures, like different water temperatures. So by looking at what kinds of shells are in each layer, you can tell what the ocean temperature was like back then.
What's amazing is that scientists figured out they could get climate information from this deep sea mud even back in the late 1800s during expeditions like the HMS Challenger. But the real revolution came with the invention of these special tools called cores that could pull up long, undisturbed tubes of sediment from the ocean floor. These cores could go back hundreds of thousands, even millions of years.
Those early gravity cores were a good start, but the Kuilenberg core, invented in 1947, that was a game changer. It could get much longer cores. And when they started analyzing these cores, they found clear evidence for multiple ice ages way back in time. Researchers like David Erickson and Goesto Wallen at Lamont Doherty Geological Observatory even found this sudden climate shift around 11,000 years ago, and they could see these long-term patterns of climate change by looking at the types of plankton shells in the different layers.
But there were problems with just using the plankton populations to figure out ocean temperatures. So in the 1950s, scientists at the University of Chicago came up with this clever method called the oxygen isotope technique. It basically looks at the ratio of two types of oxygen, oxygen-16 and oxygen-18, in the shells of foraminifera. The amount of each type of oxygen that gets incorporated into the shell depends on the water temperature when the organism was alive. So by measuring the ratio of these isotopes, they thought they had a more accurate way to figure out past ocean temperatures.
And Cicero Emiliani, he used this oxygen isotope technique to study deep-sea cores, and he found evidence for 7 ice ages and warm periods over the last 300,000 years. He thought this might be connected to the Milankovitch cycles, but his results didn't totally agree with what Erickson had found earlier with the plankton, and a lot of scientists were still skeptical about Milankovich's theory.
The breakthrough came with John Embry. He was this brilliant statistician, and he came up with this way to analyze all the different foraminifera species in the cores, not just focus on one or two. He realized that things other than temperature, like salinity and nutrients, also affected what types of foraminifera lived in the ocean. When he took all of that into account, his analysis showed that Emiliani's basic picture of multiple ice ages was right, but changes in salinity had also been messing things up. And importantly, he found that the temperature difference between ice ages and warm periods in the deep ocean was probably smaller than people had thought based on just the oxygen isotopes. This meant something else was affecting the oxygen isotope signal.
And that something else turned out to be an amazing insight from Nicholas Shackleton. He figured out that those changes in the ratio of oxygen-18 to oxygen-16 in the foraminifera shells, they mainly reflected the total amount of ice on the planet. You see, the lighter oxygen-16 evaporates from the oceans more easily and gets locked up in glaciers, leaving the oceans enriched in the heavier oxygen-18. So those oxygen isotopes weren't just telling us about local ocean temperature, they were a direct measure of how much ice there was globally, and therefore a really good indicator of global climate change.
Exactly. This completely changed how scientists read those deep-sea cores. But to really test the Milankovitch theory, they needed to figure out the exact dates of those climate shifts. They needed independent ways to check if the timing matched the astronomical cycles. Beyond carbon dating, which only works for relatively recent stuff, they started using other radioactive dating methods with longer half-lives, like uranium, thorium, and potassium argon dating. Thorium-230, with a half-life of about 80,000 years, turned out to be really useful for testing Milankovich's model over these long time scales.
And these new dating methods gave them some amazing evidence that supported Milankovitch. For instance, they used thorium dating on old coral reefs and shorelines that were now way above sea level in places like Barbados and New Guinea. These showed sea level changes that matched up perfectly with the timing of those warm interglacial periods predicted by Milankovitch. Then there was George Kukla, who was studying these layers of windblown sediment called loess in Czechoslovakia. He found 10 cycles of dust accumulation, each about 100,000 years long, which matched Milankovich's eccentricity cycle. And in 1969, Wallace Broecker and Jan van Donk were studying oxygen isotopes in cores from the Caribbean Sea. They found 6 cycles, each about 100,000 years long, with these really quick jumps into warm periods.
It's pretty incredible, right? All these different lines of evidence were pointing in the same direction. And then in 1969, there was this meeting in Paris between Broecker, who was studying the ocean, and Kukla, who was studying the sediments on land. They both realized that their findings independently supported Milankovich's theory. The evidence was really starting to pile up.
But one mystery remained, didn't it? Why did that 100,000-year eccentricity cycle seem to be so strong in the ice volume records when Milankovich's calculations suggested it shouldn't have been that big of a deal?
That's a good question. It actually goes back to something James Croll had mentioned much earlier. Even though changes in Earth's orbital eccentricity don't have a huge direct effect on the total amount of sunlight we get, they do have a big impact on the strength of the precession cycle. When the Earth's orbit is more stretched out, those wobbles in Earth's axis have a much bigger effect on how much sunlight different parts of the Earth get at different times of year.
It's amazing how science builds on itself like that. To get even more precise dates for those climate shifts, scientists also started using paleomagnetism. Basically, looking at the record of when Earth's magnetic field flipped, which gets preserved in rocks and sediments. Those magnetic flips happen pretty quickly, geologically speaking, so they're like these great markers in time. And there's this one big flip, the Brunnis-Matuyama reversal, that happened about 780,000 years ago, and that became a really important marker in those deep-sea cores.
Well, researchers at the Lamont Doherty Geological Observatory used paleomagnetism to date events in those cores, building a really detailed timeline that went back through multiple ice ages. And this led Jim Hayes to start the CLIMAP project in 1971. CLIMAP stood for Climatic Mapping Project, and it was this huge effort to bring together all sorts of scientists to make detailed maps of past climates.
And they found this one core, V28238, from the Pacific Ocean. They called it the Rosetta Stone of paleoclimate because it was so amazing. It went back almost a million years past that Brunnis-Matuyama reversal, and it had these perfectly preserved foraminiferous shells, perfect for oxygen isotope analysis.
Nick Shackleton analyzed that core and showed that those changes in oxygen isotopes really were global. It wasn't just something weird happening in one part of the ocean. Those changes in ice volume were affecting the entire planet, even the deep ocean in the tropics.
And then they did this really detailed statistical analysis on some super long cores, including one from the Indian Ocean and another from Florida State University. They were looking for repeating patterns or cycles in the oxygen isotope data, and they found clear cycles at about 41,000 years, 23,000 years, and 19,000 years. Those matched almost perfectly with the cycles of Earth's axial tilt and the precession of the equinoxes. And more refined calculations from Andre Berger had shown that the precession cycle actually has these two closely spaced frequencies, which explained why they were seeing those two peaks around 20,000 years.
All of this led to that super important 1976 paper in the journal Science by Hayes, Embry, and Shackleton, titled Variations in the Earth's Orbit, Pacemaker of the Ice Ages. They concluded that those changes in Earth's orbit are what causes the ice ages, the ones that have been happening for the last few million years. They even predicted that, based on the current orbital configuration, the northern hemisphere is slowly heading towards another ice age in the far future.
And that same year, John Mason, the head of the UK Meteorological Office, he had been skeptical of Milankovitch's theory before, but even he came around. He did his own calculations, looking at how much energy it would take to melt all the ice that melted since the last ice age. And his result agreed amazingly well with the changes in solar energy predicted by Milankovitch's model. We're talking about agreement across 24 orders of magnitude.
It's mind-blowing, isn't it? This really showed just how powerful those astronomical cycles are in shaping Earth's climate. So the melting of the ice sheets that started around 18,000 years ago, bringing us into our current interglacial, and the peak of warmth around 6,000 years ago, those were all driven by those three astronomical cycles working together. And like we said before, the conditions that make for warm summers in the northern hemisphere, those have been getting weaker over the last 6,000 years. That suggests we're slowly moving towards a colder climate and maybe another ice age way down the line.
One of the most surprising findings was that the whole planet seems to change climate at the same time. Even though the astronomical forces have the biggest effect on the northern hemisphere, both hemispheres seem to warm up and cool down together. This tells us there are these powerful feedback mechanisms, probably changes in ocean currents and winds, that spread the climate signal across the whole planet.
It's fascinating, isn't it? We started with these confusing rocks and ended up with this amazing understanding of how the Earth's movements in space drive these massive ice ages. But the story doesn't end there. These ice ages, they've probably had a huge impact on the evolution of humans, too.
Absolutely. We're mammals, and we wouldn't be here if it weren't for that asteroid that wiped out the dinosaurs 65 million years ago.
Wow.
And after that, as mammals started taking over, the Earth was slowly getting colder.
And then, around 7 million years ago, Antarctica started to freeze over. Then, about 3 million years ago, the geography of the northern hemisphere changed a lot, with big mountain ranges rising up. That's when the first big ice ages started happening in the north, around 3.6 million years ago. And this timing is really important because it lines up almost perfectly with when our earliest ancestors appear in East Africa.
Right, so when those ice ages started happening in Europe and North America, they would have changed the wind patterns all over the planet. This probably made East Africa a lot drier, with more droughts. Those changes would have had a huge impact on our early ancestors, maybe even forcing them to adapt in new ways.
And here's the really interesting part. If you compare the DNA of humans, chimps, and gorillas, it looks like our lineages split from each other somewhere between 3.5 and 4 million years ago. That matches up perfectly with the start of the current ice epoch and all those big climate swings that came with it.
So maybe those ice ages, with all their back and forth changes, they actually played a part in making us human. As forests shrank during the cold, dry times and then grew back during the warm, wet times, the apes that were good at adapting, at eating different foods and living in different places, those are the ones that survived.
It makes you think, doesn't it? Imagine those ancient forests shrinking and expanding and these early apes trying to survive. The ones that could walk upright, freeing up their hands to carry things and use tools, and the ones with bigger brains that could figure out new ways to survive, they would have had a huge advantage. And these cycles of hardship and then good times, maybe that's what drove the evolution of intelligence. We can't be 100% sure, but it's the best explanation we have right now for why things happen the way they did.
That's an incredible thought.
Yeah.
So without those ice ages, maybe we'd still be living in trees. Those harsh, changing environments might be the reason we became smart and adaptable in the first place.
Uh-huh.
And it's pretty amazing to think that modern humans, sapiens, we actually emerged during the last warm period, the one before this one. And we survived that last ice age, and then, well, here we are.
It really puts things in perspective. And that's not even all of it. We haven't even talked about how the ice ages shaped the landscapes we see today, or how they affected the distribution of plants and animals around the world. It's a truly vast and fascinating subject.
It really is. It makes you realize how much our planet is constantly changing, even on these huge timescales. And it makes you wonder what the future holds, especially with human activity now adding to these natural climate cycles.
Absolutely. We've come a long way from those early scientists who were just trying to figure out where those strange rocks came from. Now we have this deep understanding of the Earth's climate and how it's connected to the universe, but we also have this huge responsibility to take care of our planet.
I think that's a great place to leave.